So as always, if you have questions or concerns or discussions, then we can, discuss. As I promised, I'm going slowly and yet very sort of like step by steps fundamentally, so that we gradually reach to our main objects, which are the Hamiltonian systems and the Lagrangian frameworks, the minimizing problems. Um, in last week, the three lectures we were doing um, Legendre transforms, in which we only dealt with the Hamiltonian that depends on P only. And in practice, we're going to need to deal with Hamiltonian depending on space and momentum, and then Lagrangian also depending on space and velocity. So that's going to be our object today. I will discuss with you about that. Um, I'll give you a clear example about the classical mechanics framework. And then we discuss about Legendre transform for that general case. And eventually, if time permits, I'll give you a preview about, the significance that we need to know both frameworks, and so we can switch back and forth naturally. And that's sort of like the starting point. Again, do stop me if you have questions or concerns or anything you want to discuss. Um, so I recall very quickly what we did earlier. Um, you know, so last time we defined locally uniformly convex by just saying that the Hessian got to be, positive definite. Uh, and then we define uniform convexity by saying that, the Hessian has to be greater than equals to some theta times in. By that I mean that, by that I mean that the Hessian has to be positive definite. Uh, Here there is here I mean that there is a theta greater than zero, right? The Hessian has all eigenvalues that are greater than equals to theta. And then we were concerned with the fact that if the Hamiltonian is Ck for k greater than equals to 2, we need k greater than equals to 2 just for technical reasons, then everything would be preserved. The Lagrangian is also in Ck, and we have all the beautiful formula, the three formula we have here. And we would like to make sure that this is still the case when for our object today. So the Hamiltonian depending on x and p, and the Lagrangian, the corresponding Lagrangian depends, on L of x and v. Maybe let me make it clear here, and we're gonna go deeper into the details. X here typically represents for the position. You can think of the positions of a particle, or a complicated system depending, many particles. Um, then X represents for the couples of all such positions of the particles. P here, typically represents for momentum, and V here represents for velocity. So, in different textbooks, people use it differently. Sometimes people use it, uh, you know, P and Q for positions and momentum and stuff like that. I find that it's better to use X, P, and V. Okay. So again, as I said, the framework is that we're gonna consider it more realistically, that the Hamiltonian, again, H is mapping from Rn cross Rn to R, that mapping from xp to h of xp, like what I wrote there. I already wrote it, but I just want to recall it so that everything is clear. And we typically assuming that the Hamiltonian is continuous in both variables, is convex in the p variables, and is it's superlinear in P uniformly. Okay, I mean we take the infimum here, so inf in X of Rn of xp over P. Let me just explain. This just means that we want um, things uniformly in X. Okay, so what I meant there is that, you know, when you let P goes to infinity, you wouldn't want that, you know, it's sort of like not that uniform in X. So you really want this one to happen with that. Okay. um, and then naturally, you know, we don't do Legendre transform in the X variable. The X variable just stays there. So, you know, X is X, X is a set, but, you know, so I could say, okay, so X is set. So you only do Legendre transform for P changing to the V variable, okay? So you would define LXV, you know, you keep X to be the same, you just change the P variable to be the V variable. So you just take exactly supremum in P of P dot V minus H of XP. So everything looks pretty much the same. When you fix X, you know, so if you think about you fix X, then it comes back to to our first three lectures. Okay. um Nothing different here. I mean, what we really concerned about is that what's happened when they're joined, you know, there are two variables X and P, and again, that's nothing really crazy going on here, but we really want to make sure that nothing is going wrong when we consider the joint differentiability and joint properties of X and P and X and V. Okay, so here's a very beautiful example that of my interest. You know, I love this example, and actually, this example has historical significance because this is the example coming from Newtonian viewpoint of classical mechanics, and when you know, Lagrange first tried to reformulate Newtonian mechanics in terms of Lagrangian viewpoint, then this is the one. Um, so basically what you do is that, again, as I said, X is the positions, V is the velocity, and P is the momentum, and M is the mass of the particle. You know, again, you normalize it so that M is one. So you normalize it so that the mass is one. And clearly we have that, you know, we have the natural formula is that P is mv, right? This is classical mechanics. Momentum is mass times velocity. Is just, you know, the sort of like the likelihood of sort of having something force or push forward with, you know, the higher the mass, the higher the momentum is. But then when we fix the mass is of the unit, and P is equals to V, that, you know, right? And and then we have the Hamiltonian, as we have learned, this is a total energy, right? So this equals to kinetic energy and potential energy. And when you have kinetic and potential energy, uh, you know, what you want is that, you know, you try to compute, right? And we have the formula that kinetic energy is 1/2 times mv squared. But because m is 1, and again P equals to V, you know, there are difference in terms of unit, but basically if we just take away all the, you know, units and stuff like that, and this is exactly 1/2 of P squared plus V of X, right? This is the potential energy. Okay. um, and typically you're going to always see that we are not trying to minimize the Hamiltonian, because the Hamiltonian is a fixed energy. You know, we have conservation of energy. Again, this is classical mechanics. And you know, we already talked about this, right? if you have this is the Hamiltonian, well, I can even compute, right? LXP is what? LXP is just compute supremum of P in P of, P dot V minus LXV. Let's just compute. I mean, we did that earlier, but let's just repeat it once more. This equals the supremum of P in Rn of P dot V minus LXV now becomes 1/2. I'm sorry, I wrote it wrong. Sorry. P dot V minus H of XP, right? And H of XP is 1/2 of P square minus V of X, right? So you have that plus V of X becoming minus V of X, and this one is really independent of P, right? So you can just pull it out. Again, it might be a little bit boring for you guys, but believe me, I mean, once you have this, sort of clearly done and well motivated, then everything is clear. So, you can pull the minus V of X out. You just have supremum of P dot V minus 1/2 of P squared. This is exactly what we did earlier, minus V of X, okay? And this one is just 1/2 of V squared minus V of X, okay? And that's it. So that's the Lagrangian. And clearly you see that this is a difference between kinetic and potential energy, right? I mean, one way you can imagine is that you have the potential energy. I mean, it's going to create the potential field. It's already there in the environment. You cannot change it. What you can change is that the action functionals in which you try to minimize the actions, which is the difference between kinetic and potential energy. So we come back to this, but one of the key problem in classical mechanics is to minimize minimize minimized the action, right? The action you have is that maybe, okay, let me just write I typically write like minimize the I of gamma, which is equals to minimize the action functional going from A to B of L gamma S gamma dot S ds. So, I mean, geometrically, you try to go from a point, let's say Y, to a point Z, where you have gamma A is equal to Y and gamma B is equal to Z. You try to go in all various different ways to go from one point to the other. And the potential energy is given. We cannot change that, but we can change the actions, right? I mean, like how fast do you go? You can control the kinetic energy. So you try to go in such a way that you minimize your action. And that's the very classical problem in classical mechanics. So we will come back to this. And of course, I mean, this is sort of the key problem in classical mechanics, in Hamiltonian dynamics, and also in our course. And as I said, I'll come back to this later to show you right away that from here, we can reformulate Newtonian mechanics very quickly. But I mean, we are going to go much deeper than this in this class, okay? Okay, so to be back by the end of this lecture. Okay, so now let's state the theorem, and you can see that the theorem we're going to state is rather natural. It's pretty much related to what we did earlier, right? We just want to be careful again about the joint property of X and P and X and V. Okay, so theorem 1, again, we say that L is finite, it's convex in V and superlinear in V, so that's clear. And if you take the Legendre transform twice, again, only in the V variable or the P variable, right? So if you actually do it twice, it comes back to H. Everything is clear. And for X, the V, there's a vector P. And again, what is important now is that P depends on both X and V, right? So P now not not only depends on v, but it's also a function of x and v, and thus this is what I meant. This is the joint dependence. So you can find a vector p so that you have equality happens. This is also not surprising. And furthermore, if v is bounded, then the corresponding p is bounded. This is also not surprising. So this is the first new point, is that the Lagrangian is continuous in both x and v, right? It's a joint continuity that we have to be careful. The next one is that it's also a bit new. So if x is strictly convex in P, earlier we know that if x is strictly convex in P, then the Lagrangian is C1, and here is the same, right? So you're going to have that the Lagrangian is differentiable in V. Furthermore, you know, this is also new, that is jointly continuous in X and V, right? Again, it's not really new, but it's significant in the view that is continuous in both variable. Okay. So you can see that I wrote down the proof here, and I only showed number 4. Number 5 can be done in a similar manner. So I only do the point that we need to prove joint continuity. And again, we are just writing down the definitions, right? You take a sequence xk, vk that converges to xv, x bar v bar in Rn cross Rn. Okay, and surely we need to show, we want to show that L of xk vk converges to L of x bar v bar. Okay. You know, to do that, we just gonna need to, you know, basically reconsidering what we have in our mind. On the one hand, as we have stated, we already say that in earlier, right? Lxk occurs, you know, at a point pk. So I have L of xk vk equals to pk dot with vk minus h of xk pk. Okay. And similarly, I have this occurs at a point p bar, right? So again, you know, there exists pk and p bar. And furthermore, moreover, what we have is that pk and p bar are both bounded by a constant. And this is important because again, you know, vk and v bar are bounded. So pk and p bar are also bounded. So the point that they are bounded allows me to essentially, you know, pass to subsequences and have conversions and stuff like that, right? And that's essentially the point for us to go forward. So on the one hand, what we have here, you know, one direction is always easy. So on the one hand, what you have here is clear. You have L of xk vk is equals to pk dot vk minus h of xk pk. And, you know, because you have that vk is converging to v bar, right? So you can write that vk is equals to v bar plus ok of 1. You know, I'm doing it in a hand wavy way so that I can be lazy. And I have that this error is going to 0 as k is goes to infinity, right? And that's sort of the idea here, right? You know, I'm replacing here. I'm replacing in here that I'm replacing vk by v, right? And when I replace vk by v, I have to pay a price of an error term. Again, remember that pk is bounded, so I don't have to pay too much. It's just analysis here, right? And then going from this inequality to this inequality down here, I'm just using the fact that L of x bar v bar is a supremum OP, right? So for one particular pk, then surely it's less than equals to that. So I have clearly that I have L of xk vk is less than equals to L of x bar v bar plus an error term, right? Hence, I have lim sup of xk vk is going to be less than equals to L of x bar v bar. I have this box, right? Yeah, clear?
Can I ask a question about this? So in that second step there, we also replace the xk with the x bar, right? So I guess there's some
Yes.
continuity of h, I guess.
Yes.
Okay.
Oh, I'm sorry. I'm sorry. No, you're absolutely right. I mean, I should have mentioned here as well that uh, that xk is equals to x bar plus ok of 1 as well. So you're absolutely right. I wrote it up here that we needed to assume that h is continuous in both variable, right? So that's really important. So the continuity in joint in x and p implies the joint continuity in x and v. Okay, so that's really important. Otherwise, I wouldn't be able to do that. Um,
Or
so
maybe do we need some kind of uniform convergence or uniform continuity since we have x bar pk going to.
no, pk is bounded. Pk is bounded.
Oh, I see. Okay, yeah.
Yes. So everything is in a compact set here, and that's why uh,
I
that's
see.
why it's important. Yeah.
Okay, I think they.
Yeah. Thanks. And again, later on, we're gonna assume more, but you're absolutely right. If I don't have PKs about it, then I would have to be careful. Okay. Yeah. Thanks a lot. So clearly, then I have one-sided inequality that lim sup of L x k v k is less than equals to L of x bar v bar. And for the other directions, then, again, as I said, in this proving this kind of business, one direction is always easier than the other. Uh, of course, in this case, both are rather straightforward. Um, so the other direction is a little bit easier. Why is it? Because, I mean, what you have is that you just write out the formula, right? L x k v k is the supremum of this one. And what you would do is that you just plug in one particular choice of p, which is p bar. So I have this is greater than equals to p bar of vk multiply, p bar dot vk minus h of xk p bar. Okay. And now again, what you have here is that you have p bar dot with vk minus h of xk p bar. And when you let k goes to infinity, this converges to nothing but p bar dot v bar minus h of x bar p bar, right? Because we have continuity in vk converging to v bar and xk converging to x bar. And this is nothing but L of x bar v bar, right? And then that means that we are done. Okay. Um, so it's not hard, as I said. I mean, we just need to be very careful so that the joint properties of x bar, xv and xp are preserved. Any other concerns? And as I said, I mean, we have to be very careful from the beginning that we have everything is bounded so that things are in compact set. And that's why we have uniform continuity. Otherwise, we would need to assume it, right?
Yeah, could we say so? I wasn't quite sure why if the v is bounded, then also that implies that the p is bounded.
Yeah, because we proved last time, right? Okay. So remember, okay, so that's a good question. Maybe I can recall it here. Okay. So let me maybe make a remark. So again, recall the definitions of Lxv. This is equals to supremum of P dot with V minus H of xp. Okay, and let's say that this occurs at a point P xv dot with V minus H of x P xv. Okay, so so this happens at Pxv, and we know that Pxv is in a subdifferential of h h at um, no v. Sorry. This happened at a point at which V is in the subdifferential in P of H at XP XV, right? Because you are trying to minimize the things, and this one happened only when V is in the subdifferential of P at H of XP XV, and this is also equivalent to the fact that P XV is in the subdifferential in V of L at XV, right? That's the thing, right? Okay. Now again, I mean, if you recall, maybe a picture would help here. Maybe this is LXV. LXV. Okay. When X is fixed, this is the map in V. This is LXV. Maybe this is your V. Okay. So you see that P is somewhere here. P can be some of the values. P need not to be a unique value, but clearly, we proved earlier that if P is in this gradient, you have L of XV plus H is greater than equals to L of X V plus P XV dot with H, right? For all H. So, I mean, earlier we proved that then you can have that PXV, this is the maximum of H less than equals to 1, PXV dot with H. And clearly this is less than equals to maximum of all H less than equals to 1 of, just take everything you want, LXV plus LXV plus H, okay? And now you know that V is bounded, right? If V is bounded by C, then the right-hand side is bounded. Does that
I
make
see.
sense?
Yes. Thank you. Yep.
Okay.
Thank you.
So this is important, and then it's great. It's great that you guys asked, and I really want the lecture to be like this because you see that we built everything up from the beginning. So you see that if V is bounded, then PXV is also bounded. And you can even write out the constant, right? So PXV is bounded by twice times max of LXV for V less than C plus 1 or something like that. So it's just a very clear constant, okay? Okay. Right, so you see convex analysis is very beautiful here. I mean, convexity to me is quite rigid, and somehow you can exploit a lot of properties from convexity. Okay, cool. Is it clear? All right. So now let's do theorem 2, and again, I really like the fact that we can discuss deeper, and sometimes you see that sometimes I'm also a little bit like quick, so do stop me, and sometimes I'm not careful when teaching, also when doing research, and it's good that I have to be careful all the times. All right. So the theorem saying that if H is in C-K in both variable jointly, then we have L is C-K in both variable jointly. It's really beautiful. I mean, it's that we can preserve everything. It's jointly. And surely, I mean, if they are differentiable, then you have seen that P is unique. There's a unique P, so that this is the case. And moreover, not only that is unique, we have the computation, right? So dV in L is PXV. So those two things, and the Hessian is the inverse of the Hessian in H. Those two things are old. The new thing is the second line. The second one is new and it's extremely important. This box is new. So this is new point. And I would say that this new point is rather important. What it says is that when you take dx in L, it's minus dx in H, computing at x and p x v. Okay, and this is important. Okay. Now let's go back to the example. This is obvious from the example, right? You know, in the example, if I have H is plus V of X, and dx in H is dV of X, right? And if you take L, it's minus V of X. So that's clear from the example. Because, you know, essentially when you take the Lagrangian, you subtract the thing with X, so, you know, you have to change the sign of the potential energy, essentially. Okay. It's natural from the example, but it's really important in the general setting, and we need to prove it. That's how I would say. And the final point here is obvious. It's just the duality. You know, if P is dV, then V is dP. Again, it might be simple, but to me this is always a mysterious thing. It's just the duality is really strong. Okay. So now let's prove what did I say? What I said here is actually not very correct. So I said that we only show that L is in CK, but that's not just that. I mean, not just that to show L is CK. I mean, let me highlight it right away. What is really important is this last line here. The last line here implied both. The last line here that I highlighted, I mean, it's important that we have exactly the property, the new point that we have. Dx in L is minus dx in H. And let me say it right away that this implies what we need, right? Okay. So what do we need? To prove L is in CK, you know, if you fix the X, you only vary the variable P and V, then we have done it, right? This is what I said. We have already proved that if you fix X, then L is CK in V by the previous lecture. That's not a big deal. Moreover, we also have proved that Pxv is in CK minus 1. Why is it so? It is so because you have Pxv Pxv is dV in L of xv, and V is dP of hp, and you know this is the CK minus 1. So basically this implies that you have dV in L is CK minus 1. So that's not a problem. Okay. So maybe let me write down so that is clearer. I have Lxv is Pxv dot with V minus H of X Pxv. Okay. So what I have here is that, you know, as we have said, what I have here is that this is CK minus 1. This is not a problem. V is V. V is just a vector. This is CK minus 1. H is CK. Okay. So clearly from here, like the last remark I made last time, it's not very clear for me that I have L is in CK, right? From here, what I can deduce is that L is in CK minus 1 of Rn cross Rn. Okay, this is not hard. This is what I can deduce right away. However, to go that from L is in CK minus 1, so this is what I said, to L is CK, then I have to be a little bit more careful, right? To do that, I would need to show that this is the case. I mean, this equality that dx in L is minus dx in H, and because H is CK, right? So because h is ck, so minus dh in x is ck minus 1, right? So if I can show this equality, then I would imply that dx in L is also ck minus 1, and then I would be able to conclude my proof, right? That's pretty much it. So there are many ways to prove this equality. Actually, I chose the maybe the easiest one. I don't know, maybe it's the easiest one for me. How do I prove it? I mean, you can choose other ways actually, but the easiest one is that we have a formula, right? So why not just differentiate it in x? That's pretty much it. So if you differentiate it in x, you have, you know, on the first hand, this terms here gives you what is down here. Okay, so dx in p of xv times v. Okay, again, we have to understand this in the fact that this is dx in p is a n by n matrix, and we multiply with v, so v, I think of it as a column vector here, right? Okay, so I have a matrix multiplied with a column vector. This is fine. And then if I differentiate in x, I would have this one, so just dx in h. That's that. But if I differentiate in the other variable in p here, then I would have to use the chain rule, right? So I would have to differentiate dx in p, multiply with dp in h. Again, here you see that I switched the order because I think of dx in p is an n by n matrix and dp is a column vector. It's just a matter of writing. Okay, and if you recall, dp in h is just v, right? So this is v. So you see that I have these two factor cancel out. These two comes together and give me 0, right? So they cancel out beautifully. It's really that the duality property is hidden here so that I can cancel things out. Okay, so when I can cancel things out, then I am good. I have the formula I need, right? So I have dx in L of xv is minus dx in h of xp xv, and I have that is ck minus 1, and it's beautiful. Is it clear? Any question for me here?
A question. So why was it important to know? So I see the second step. Why was it important to know that ck minus 1 was at least, or why L was at least ck minus 1?
Okay. Very good. It's very good. So because I know that it's at least ck minus 1, I can okay. So so to do this, I would need L at least C1, right? So that I can differentiate.
Oh, I see. Okay.
Yeah.
I see.
Just to differentiate without any justification. Otherwise, I wouldn't need to justify, you know, like maybe taking the difference. There's some books that they can take the difference and they pass the limit, but you know, we are just being lazy here. We just use the fact that it's at least C1, so we can just differentiate without violating anything. Okay. Again, this is the easiest way to me, because when, you know, for analysis and PDE, one of the trick is that whenever you can differentiate your equations as many times as you want, just differentiate. You know, maybe sometimes things are canceling out, and this is actually most of the time is the key point of analysis probability and PDE, is that sometimes there are magic cancellations, that some very bad things, but you know, when you mess around, we can cancel out many things that you end up with something beautiful. And you see there's a magic cancellation here, right? It's there because actually we have the duality equality, you know, that dp is dph is v. That's why we can cancel things out. Okay, all right. So great. So that's an important question. As I said, I'm not doing quasi-convexity here. So by this, we are done with chapter 1 of Fathy. If you look into Fathy's book, he did it in a very different way. So I prove everything, all the results that I needed, but I prove it in my way using, my book and also some other textbook of maybe like Kanasa Theory and other books that are more standard. Fatih has to do that for manifold, so that's sometimes has to do it for local, like local results. So it's harder. And the ideas behind are the same, but it's more technical. But I mean the take home point for us is that CK property is being preserved under the Lagrange transform for k greater or equal to 2, and everything is nice. And as I said, for a deep characterization of Lagrange transform, that this is rigid, this is unique, essentially. If you have certain properties and if you take the transform twice, you get back to the functions, and it has to be Lagrange transform. It's very beautiful. Any other concerns? Okay, so so let me give you a very quick preview. So so quick preview of the duality between Hamiltonian ODEs and Lagrangian viewpoint. This is not new. This has been known for a long time. Again, we are covering everything from the beginning. So in the next few lectures, I'm gonna do this viewpoint. I'm gonna prove some deep results that concerns existence of minimizers and then regularity of minimizers. So as I said earlier, the key problem in calculus of variation in classical mechanics and optimal control and some other fields is just a very simple problem of minimizing the action functional of a curve gamma with gamma a equals to y, gamma b equals to z, integral from a to b, L of gamma s, gamma dot s ds. So again, gamma a equals to y here, gamma b equals to z here. I will repeat this point many times in next few lectures. So you are free to choose which part you take, and you are trying to minimize your action. Okay. So we're gonna say that we're gonna show that this problem has a minimizer. Okay. Let's just say that it's going to be C. So C is a minimizer to the problem. We're going to prove this technique by using calculus of variation and prove it quite deeply. And we're going to also show that and C is CK. So it's really smooth. It's as smooth as your Lagrangian and Hamiltonian. Beautiful. Okay. So not only that you have a minimizer, but it's CK. Okay. And then we're going to show that by using calculus of variation. And I show that C satisfy the so-called Euler Lagrange equations. We're going to prove it. Don't worry. I mean, this is just a preview that I have d over dt of dv L of ct c prime of t equals dx L of ct c dot of t for a less than equals to t less than equals to b. Okay, I'm gonna have this Euler Lagrange equation. Okay, I'll come to the example for a moment. Now, what's the deal here? That what I meant that we can go from so this is a Euler-Lagrange equation. It's very famous in many different fields, in calculus operations, physics, optimal control, PDE. What is remarkable here is that you have dv here, okay, and dx here, okay. And this is from Lagrangian viewpoint. Those are there, okay. But what is remarkable here is that if I let xt is just ct, that just basically position of the particle, of our particle. You can say that your particle is going from y to z, trying to minimize its action, which is a normal, first principle in physics, whatever, right? And what is remarkable here is this is nothing but pt, right? Pt is dv of L ct c dot of t. It's exactly the equality happens for our Legendre transform, right? If I let P is dV, then essentially this is equivalent to the fact that C dot of T is dph of xt pt, okay? This is a dual formulations, right? And C dot is what? C dot is x dot, right? So this gives me that I have x dot of t is equals to dph of xt pt, okay? So that's the first relation. The second relation is, what is p dot of t? P dot of t is exactly this PDE, this calculus of variations equations, right? P is the dv, right? So P dot of t is d over dt of pt. So P dot of t is dx L of ct c dot t, okay? That's that. But remember, this is exactly that what we just proved here, right? This is the box that I just put it here. It's the important new point here. Dx of Lxv is minus dx of h of xpxv, okay? So this is nothing but minus dx of h of xtpt, okay? So from the Euler-Lagrange equations, it turns out that this is equivalent. So Euler-Lagrange equations above, this is equivalent to the system x dot of t equals to dph of xt pt, and p dot of t equals to dx minus dx of h of xt pt. And this is nothing but exactly the system of Hamiltonian ODE. ODEs. So you see that you can go and back and forth, and the two viewpoints essentially are dual, but they are the same. And this is amazing because Hamiltonian ODEs is the core of, again, Hamiltonian mechanics, core of symplectic geometry and other fields. And of course, we are not just stop here. We're going to go much deeper. You're going to see as time goes, but at least I hope that you see why we had to spend 4 lectures to do the duality, right? Because the duality occurs already when have dvl is p and vice versa, right? So p equals to dv of lxv, meaning that v equals to dp of hxp, okay? So the last minute, so last point for the last minute. So the Euler-Lagrange equation, let me recall, you have d over dt of dv of L ct c dot of t equals to dx of L ct c dot of t. Okay, so that's our Euler-Lagrange equations. So back to the example we have earlier. Lxv is 1/2 of v square minus v of x, right? That was the example we have earlier. So in this example, what do we have? That means that I have d over dt. dv is going to be v then, right? So dv of L is v. dx of L is just minus dv, big V. Okay. So dv of L is v, so that means I have d over dt of c dot of t equals to minus dv at ct. Okay. So that means I have c double dot of t equals to minus dv of ct. Okay. If you think about this for a few hours or whatever, this is exactly Newton's law, right? V is the potential. So by steepest gradient descent minus dV, this is the force, right? Or you know, the force of the potential field. I mean, the potential field, whatever, right? I mean, you have potential, then going in the minus of the gradient direction is the direction that it changes the most, right? Decrease the most in terms of the temperature. This is what? This is MA, right? So I have F equals to MA. M is 1, remember, right? Acceleration is just double derivatives of the part. So that's the reformulation of Newtonian mechanics. Is it clear? Yeah. So again, it's beautiful. Surely we're gonna do this carefully. I'm just giving you a preview. Sorry, it's taking a bit further than a little bit more than the usual time. So I'll post the post lecture notes and the videos shortly. See you on Wednesday. Okay. Have a good week. Bye for now.